Hello, everyone. My name is Joe Menke. Today I present the work of myself and Doctors Oziert, Bandrowski, and Martone. This is regarding the detection of anatomical and functional connectivity relations across the biomedical literature via language representation models. This research was conducted with backing from the SPARC program and support from the NIH Common Fund. Special thanks to the Google TensorFlow Research Cloud program for providing free TPUs, which we use to pre-train our lecture models. So, I just wanted to run through a quick outline of the presentation. I'll start with the background and then move forward with our immediate motivation and goal for this project. I'll cover how we generated our vocabulary set and corpus, and then I'll cover a little deeper some of the specifics of our annotations there. Next, I'll go through the models we trained and ended up using, as well as their performance on our relation extraction task. I'll discuss our use of active learning and hyperparameter optimization within our models, and then finally, I'll briefly go over conclusions and cover where we plan on going next. Alrighty, well, a good start in terms of background is defining who we are and what the SPARC program aims to accomplish. The general goals of the program are to provide a solid scientific foundation to drive innovation in the development and advancement of neuromodulation devices and stimulation protocols. Neuromodulation is an emerging therapeutic approach to treat diseases of the autonomic nervous system. These aspirations rely on the foundational knowledge of bioelectric medicine, which represents the convergence of molecular medicine, neuroscience, engineering, and computing. When utilized together, this knowledge can help develop devices to diagnose and treat diseases. One goal of this project, which was our primary motivator for this particular work, is to eventually deliver detailed, integrated, functional, and anatomical maps and models of the peripheral nervous system and its innervation of target organs. An example is shown on the right, represents the Keith's bladder model, and was created using the App Anatomy modeling platform, which was developed by Dr. De Bono and colleagues in 2012. Modeling platforms like this one, which are computationally accessible, will become increasingly important if we wish to derive more utility from future medical diagrams, which are still too often simply printed on paper. To accomplish this, though, we will need to expand upon SPARC's ever-growing knowledge base. Alrighty, so our primary motivation here was to expand SPARC's knowledge base of neuronal connectivity statements and relations. We were already aware that many papers contain information on individual nerves and their pathways. This is really helpful knowledge that could be used to improve bioelectric treatments. Unfortunately, though, much of this knowledge is hidden within the millions of papers making up the biomedical literature, and this number is obviously only continuing to grow as more and more research is published every year. Furthermore, to our knowledge, no systematic approach had ever been attempted to bring this kind of information together, despite its potential impact. Because of this, our goal was to develop a relation extraction system that can pull sentences containing information on neuronal connectivity within the autonomic nervous system from the entire biomedical literature. All right, so to create our initial vocabulary set, we relied on the anatomical experts of SOG. This stands for the SPARC Anatomical Working Group. Terms were pulled in from existing ontologies like FMA, Uberon, and the NIF standard ontology. These terms were detected by longest phrase match from roughly 4 million full-length PMC open access articles downloaded November 2020. All sentences mentioning at least two distinct anatomical structures from our vocabulary set were selected. To focus our curation efforts to a smaller, more manageable portion of sentences, a smaller vocab consisting of only ANS, nerve, and ganglion terms were selected by SOG. Since the resulting candidate set was still too large for curation, we randomly sampled up to 3 sentences containing a unique term to create our base corpus of 808 sentences. Initially, 3 curators annotated this corpus together. 2 curators did the majority of curation, though. We worked in roughly 100 sentence iterations using our relation types that are defined on the table to the right. Our focus was on optimizing our models for functional and anatomical relations. During our first iteration, we only defined relations as functional, meaning we saw some sort of physiological connection. Anatomical, where we just saw a physical connection with no underlying functional relationship. And lastly, no relationship, which is self-explanatory. We discussed disagreements between each iteration, the curators. After our first iteration, we agreed to add some new entity types, structural, topological, and general. This was done to further clarify our functional and anatomical relations. An inter-curator agreement score was calculated after each iteration to determine model feasibility. After 2 iterations, we were able to achieve a satisfactory performance when we collapsed all non-functional and anatomical connectivity relations into each other. So this would be considering structural, topological, general, all collapsed down the same. Doing this, we achieved an inter-curator agreement of 91.2% and a Cohen's kappa of 0.55. So in total, we pre-trained 4 electron models on the biomedical corpus. These models are described in detail in the table below. As demonstrated by BioBERT, domain-specific language representation models improve performance on downstream NLP tasks. This is why we chose to pre-train our own models. Electra was chosen over BERT, as it has been shown to outperform on many NLP tasks. BERT uses mass language modeling, which is where the model tries to reconstruct a mass token, whereas Electra uses replace token detection, which is where a BERT-like small generator network replaces all tokens with plausible alternatives, and then a discriminative model tries to predict if the token was replaced or not. And then our corpus consists of 12.3 billion words and is made up of 21.2 million PubMed abstracts downloaded on January 2021, and roughly 4 million full-text open access PMC articles, minus the reference sections, which we removed. We used the sentence piece byte pair encoding model to generate a domain-specific vocab piece, or generate a domain-specific word piece vocabulary. We then trained our models using 1 million steps on PubMed abstracts, followed by 200,000 steps on the PMC open access text. Now, how did they perform? Well, here's a table of the performances for comparison. Unsurprisingly, the BioElectra base model outperformed the BioBERT model. And then one important thing to note regarding our model performance is that both BioElectra mid and mid combined outperform BioBERT despite BioBERT having 60 million more parameters. And as smaller models are generally better, as they're more practical to deploy and utilize in real-world applications. So we see this as a important result. In the end, though, BioElectra base containing 110 million parameters performed the best, achieving state-of-the-art performance in this biomedical relation extraction task. In our next experiments, we exclusively use this model. After settling on a pre-trained model, we focused on maximizing our prediction performance while minimizing curation effort. We randomly selected 250 sentences and strategically selected 250 additional sentences using uncertainty sampling, where we chose the 25 sentences closest to our decision boundary over the course of our iterations. This would be 0.5 in our case. These were used to test our active learning enhancement. These sentences were annotated as normal, and as shown in the graph on the right, we were able to significantly improve our model over the course of our active learning iterations. And then as shown in table 4, active learning significantly outperformed random sampling. So the additional 500 sentences we annotated during our active learning enhancement were added to our initial 808 base sentences, creating our final annotated corpus of 1,308 sentences. We performed our hyperparameter tuning using an 80-20 split, with 80% going towards training and 20% going towards testing. We used the hyperopt Python package to optimize our F1 values using learning rate and number of epochs as hyperparameters. And as shown in table 5, hyperparameter optimization significantly outperformed our defaults. In summation, we introduced a labeled autonomic nervous system connectivity relations corpus and 4 biomedical domain pre-trained Electra models. Using our labeled corpus, we achieved a high performance on a 3-class BioElectra classifier, whose performance is shown below. Based on the observed benefits of active learning, we plan on using our BioElectra-based relation extraction system in a web-based tool for connectivity knowledge-based construction with an active learning-based continuous learning ability. We hope to eventually use this data to help create advanced wiring models, making use of the App Anatomy platform described very briefly earlier. And then that's the end of our presentation. If you have any questions, we'll be available to answer anything at the poster session. And if you'd like more information on the Spark project, please visit sparc.science. And thank you.